Hello there, Mr. Sutton here with the BC Calculus 8-4 Part 1 homework solutions on vector-free response practice. For this problem, we have an object going along a curve, and we're given the dx over dt and dy over dt for this thing. And at time 0, we're at the position negative 13.5. They give us another time, sort of, kind of. At time 2, we're at point P, where they only give us the x-coordinate. So, based off of all this, we want to start by getting the acceleration vector at time 2 and also the speed. Note there's two different things on this part of the problem. So to get acceleration vector, we just need to take the derivative of the velocity vector and then plug in 2. Now, these functions aren't super nasty. I mean, this second one is kind of gnarly. This first one's not so bad. But since this is a calculator problem and they just want the acceleration vector at a specific time, we just need to take the derivative at 2 of x prime and y prime. So we need x double prime of 2 and y double prime of 2. Let's go ahead and do that on the calculator. So I'm going to start by entering these two functions as y1 and y2. So y1 is x prime and y2 is y prime. And now I'm going to quit to the main screen and actually take those derivatives. To take the derivative of x prime at 2, I've got math 8. I've got y1 here, x equals 2, and that's going to equal, 0 apparently. Okay. I mean, you probably could have figured that out just by taking the derivative and plugging in 2. But anyway, we've got 0. Let's do y double prime of 2 now. So to do that, it's actually a pretty quick process. Let me just steal my input from earlier. And this is exactly what I need, except I don't want y1. Now I want to do alpha trace y2 because that's where I stored y prime. So this is y double prime now that I'm taking at 2. And that's going to be negative 1.882. So there's the other half of our acceleration vector. Next, we still want the speed at time 2. So I'm going to need the Pythagorization of my velocity vector here. So in other words, square root of x prime of 2 squared plus y prime of 2 squared. Let me go ahead and do that now. So here's what that looks like on my calculator. x1, or x of x prime of 2 squared is basically y1 of 2 squared, because that's where I stored my x prime function. Y prime of 2 squared, that's going to be y2 of 2 squared. Again, I stored my y prime as y2. Pressing enter on that, I've got about 12.329 and some change. We'll call it 330 for those last 3 decimals. And there were no units on this, so I'm done. For this part here, I want to find the y-coordinate of point P. So to do that, I need to have a starting point. They told us at time 0, the y value was 5, and the point P happens at time 2. So I need to use my fundamental theorem on this one. I'm going to say y of 2, the p-value, the y-coordinate of the p-value, is going to be my initial y value of 5, plus, well, we're going from time 0 to time 2, so I need an integral from 0 to 2 of the rate of change of y. That'll give me the total change, adding that to the 5. So that's going to be y prime of t dt. And this is completely on the calculator after you write this. So I've got 5 plus integral 0 to 2. And again, y prime, I stored that as y2. Enter. Gives us about 13.671. For this part of the problem, they want the equation for the line tangent to the curve here at P. So for tangent lines, we need an x value, a y value, and the slope. Well, the x value they sort of gave us here. They said at time 2 the x value was 3. So we'll use 3 in our tangent line formula. We also just found the y value in part B. Again, that was about 13.671. We can use that with 3 decimals there. We still need the slope, though. We need dy over dx at time 2. Well, to evaluate that at time 2, that's going to be y prime of 2 over x prime of 2. So this is just your standard parametric slope formula here, or parametric rate of change. So let's plug that in the calculator. On my calculator, I used fancy fraction, and then I did alpha trace y2 of 2 over alpha trace y1 of 2, because that's y prime and x prime on the calculator. Enter. about 0.236 rounded to 3 decimals. So plugging everything in my point slope formula, I've got y minus the y value 13.671 equals my slope of 0.236 times x minus my x value of 3. For this last part of the problem, I want to know at what t values, if any, is the object at rest with explanations. So at rest means that x prime and y prime have to both be 0 at the same time, because then there's neither horizontal nor vertical motion. I'm going to start by figuring out what values make my x prime 0. And the reason I'm choosing x prime rather than y prime first is x prime I could actually figure out what zeros this out without having to use the calculator. It's a pretty quick process. So let me set x prime, all of this stuff, equal to 0. And let me just factor out a 3t from this. So that's going to give me 4 minus t. And then I very quickly see that the values 0 and 4 are going to zero out my x prime. All I have to do now is plug these into my y prime to see if either of these also give me 0. So I'm going to do that on the calculator. We'll start by doing y prime of 0. So plugging that in using my y2 where I stored y prime, that's going to be about 5.549. Now significantly this is not 0, so that means my object is not at rest there. So that means it's going to be 4 or nothing. All right, so let's do y prime of 4 and see what that comes out to. Back on the calculator, let me just go ahead and yank my input from before, because instead of y2 of 0, I want y2 of 4, and that's going to be exactly 0. Nice. Well, since that's 0, that means that we are at rest at time equals 4. For this free response problem, calculator-based, we have a particle moving in the xy plane with x of t and y of t as the parametric functions. They gave us the derivative of x right here. They did not give us the derivative of y. However, they did actually give us a graph of y, which is kind of interesting. And they told us at time 0 the particle is at position 5, 1. All right, so first part here, they want the position at time 3. So let me get an x and a y value separately. For the x value, I'm going to have to use the fundamental theorem. I've got an initial position and the derivative. So I have x of 3 equals the initial value of 5, plus I need an integral from, let's see, 0, the starting value, to 3, of dx over dt, or x prime of t dt. And now let me do that on the calculator. Before I do anything else, I'm going to put this dx over dt function as my y1 on my calculator, so I never have to write it again. And now quitting out of there, I've got 5 plus math 9, and we're going 0 to 3. Let's see, alpha trace y1 dx all comes out to roughly, drum roll please, 14.377. So that's the x value of my position at time 3. For the y value, I actually have to look that up on the graph here. So y of 3, that's going to be the output value for this graph when I plug in 3. So I've got an input value of 3 right here. The output of the graph, this looks like it's negative 0.5. Do we know that for sure? Well, this is a line going from negative 1 to 0 over 2 here. So this is a slope of 1/2. So yeah, that would bring us to negative 1/2 right there. Okay, so we can read that right off the graph. That's negative 0.5. Our position then is just 14.377 comma negative 0.5. For this part of the problem, we want the slope of the line tangent to the path of our particle at time 3. So we need dy over dx evaluated at time 3. Using our parametric derivative form here, that's going to be y prime of 3 over x prime of 3. Now x prime of 3, we're all set on that one. We can just find that on our calculator using the function we already entered in our y1. Y prime of 3, we're going to have to look at the graph. So for y prime of 3, looking at the graph, what is the slope at 3? Well, we already kind of talked about this in part A. This is a slope of 1/2 along this line. So we'll plug in 1/2 for that. Let's do this on the calculator now. So here's what I've entered in my calculator. I did a fancy fraction and then another fancy fraction to get 1/2 in the numerator there. That's my y prime of 3. And then x prime of 3, that's just y1 of 3 on the calculator for me. Enter, about 0.050, rounded to 3 decimals. So for this part of the problem, they want the speed of our particle at time 3. That's going to be the square root of x prime of 3 squared plus y prime of 3 squared. Let's see what that looks like on the calculator. So on my calculator, I've got square root x prime of 3, that's really y1 of 3 because that's where I stored x prime. And for y prime of 3, remember from part B, that was just the slope at 3, which we said was 1/2. So I'm really just squaring 1/2 here. And press enter to see what the final output is. That's about 9.969. On this last part of the problem, we want the total distance traveled by the particle from time 0 to 2. So we're going to need an integral from 0 to 2 of the speed that we just talked about in part C. So that'll be square root of x prime of t plus y prime of t, and both of those are actually being squared inside that square root. We have a dt there. Let's enter this in the calculator now, since we've actually already defined x prime of t, and y prime of t, well, actually, we haven't defined that yet. So we're going to have to do a little more work on this one. The problem here is that, x prime of t is defined right here. Y prime of t, that's the slope of this graph. And the big issue is that slope changes depending on which one of these segments you're on. So if you're going over the interval from 0 to 2, you've got this first segment here on the interval from 0 to 1, and then you have this other segment on the interval from 0 to 2. That means we're actually going to have to split this into 2 integrals because we have a completely different y prime depending on where we are. So I have the integral from 0 to 1 of, and I'm going to have square root of, x prime of t squared plus slope of y, that's going to be -2 that I'm squaring inside there. And now I have to add an integral from 1 to 2 of square root of x prime of t squared plus, this is now going to be 0 squared for that slope. Let me run all those numbers on the calculator now. So here's my first integral, 0 to 1, square root of, this is x prime of t squared. This is our -2 squared. And now we're going to add another integral. Let me do that off camera. Here's my other integral from 1 to 2. We still have x prime of t squared. Now we've got 0 squared, which I didn't really need to write, but whatever. Pressing enter on all that. That's about 4.34, let's round it off to 350. So there's our total distance traveled. For this calculator-based free response, we have a particle moving with parametric equations x of t and y of t. Here's x of t, and y of t is not explicitly given. Well, that was nice of them. So we've got meters, we've got seconds, we're probably going to have to use units on our answers, and we finally know the derivative of y. So we don't know the original y parametric, but we know y prime. All right, so based off all this, we want the speed of our particle at time 3. So for that, we need to take the derivative of position. So we need velocity components. We need to square those and add them together and square root it. So we need the square root of x prime of 3 squared plus y prime of 3 squared. So here's some good news. We already know the derivative of y. It's right here. So we can just write y prime of 3, and they know exactly what we mean. We can do that on the calculator. More good news. Although we don't know x prime, we could find it, but really we're just taking the derivative at a single spot, 3. So you can actually just write x prime of 3 and do that on your calculator. Let's go ahead and do that now. To make my life on subsequent parts of the problem a little bit easier, I've taken the liberty of putting x of t as my y1 and y prime of t as my y2. And I just have to remember one of these is a derivative and the other one is not. All right, quitting out to the main screen. To do x prime of 3, I need to take the derivative of this thing. So let me do a square root. And then to get x prime of 3, let me do math 8. That's a derivative. We've got dx. I need alpha trace y1 to put my x of t function in the derivative there. and then I need to evaluate this at 3. And when all is said and done, I can't forget to actually square that, so let me square all of that stuff. Okay, let me add now y prime of 3. I can just do alpha trace y2 of 3. That's going to be y prime of 3. And then I can just go ahead and square that, press enter for all of this craziness. And that's about 2.828. And let's see here, that was speed. So that's going to be meters per second for the units on that. For this next part of the problem, I need the total distance traveled by my particle from 0 to 4 seconds. So this is a little bit of a game changer. I'm going to need basically the integral of speed from 0 to 4. But in order to use x prime in general, like x prime of t, I need to actually define it. I mean, saying x prime of 3 and doing that on my calculator was fine because that was just a one-shot, one-spot sort of deal. But if I'm using x prime of t over a whole integral, I need to tell people what it is. So x prime, that's going to be 2t minus 4. I know that was so painful to do. So now let's set up our total distance formula. I need an integral from 0 to 4 of essentially the speed. So square root of x prime of t squared plus y prime of t squared, all of that with a dt. Let's do that on the calculator now. And to make my life maybe a little bit easier, I'm not really sure at this point, I'm going to put my x prime as my y3 here. So quitting out of all that, I've got math 9 to get my integral. We're going from 0 to 4. I've got a square root, and x prime, remember that was y3, so alpha trace y3, and let me square that, plus y prime, that was going to be alpha trace y2. That's where I stored that one. Square that. dx. And press enter for the whole thing. And let's see what the calculator comes back with. This is going to be in units of meters because it's total distance. So 11.588. And again, meters. For this part of the problem, they're telling us to find the time between 0 and 4 when the line tangent to the path of the particle is horizontal, and then is the direction of the motion left to right at that time with a reason. All right, so if we want a horizontal tangent line, we want to have a y prime being 0. We want no vertical motion, and we want x prime to be equal to something that isn't 0. So we're going to start by setting y prime equal to 0, solving that on the calculator, and whatever value that gives us, we'll plug it into x prime to see what direction we're going. So let's go to the calculator now. My first stop on the calculator is going to be my y equals, because I've got a y prime in here, but I've got two other things that I don't really want to graph. This first one was x of t. Let me unselect that. This next one was my y prime. Let me keep that selected. And then this last one was x prime. Don't want that. And let's see, I want to graph on the window from 0 to 4. So window, and then 0 to 4. Zoom fit, and let's hope for the best. All right, so there is y prime being graphed. And we see there's only one place where this equals 0. So that's going to be the time that our horizontal tangent's happening, assuming that that t value doesn't also make x prime 0. So let me do, let's see here, second trace, 0, option 2. And we click a little bit to the left and move over and a little bit to the right. Enter one more time. And that comes out to about 2.208 or 27079 if I round it off. So I'm going to call that A, both on my paper and on the calculator, and I'm going to store that. So going back here, let me immediately quit out of this and click the stow button. Let me do alpha A to store that. All right, now we're good to go. So at this point, I'm going to go ahead and plug this into x prime to see if I get positive, negative, or 0 out of that. Oh, and one more thing before I do that. So they gave us units. We got to give them units. Time is in units of seconds. There we go. All right, so plugging A into x prime. Let me do that on the calculator. Now, x prime, remember, we stored that conveniently as our y3. So let me do alpha trace y3. Open that up, and let's do alpha a. Close that and enter. Gives us about 0.416. So the key here is that this is, first off, not 0, so that means we've got a horizontal tangent going on, and also it's greater than 0. Since our left-right motion derivative is greater than 0, that means that we are moving to the right. For this last part, we've actually got 3 parts here. They just threw it all at once at us. So there's a point they're saying with an x-coordinate of 5 through which our particle passes twice, and they want us to find a whole bunch of stuff. First off, the 2 values of t where that happens. So let's start there, and then hopefully that'll help us out with these other things they want. So let me start by setting x of t, which is defined up here, equal to 5. And let's see where that intersects on the grapher. First, let me pay a visit to my y equals to make sure I'm graphing the right stuff. So I'm going to select this first one, y1. That's where I stored x of t. I'm going to deselect this one. This was my y prime from a previous part of the problem. And so I'm just graphing this. Let me do, let's see here. My window was 0 to 4. I'm going to keep that and see if there are 2 values of t where that works out. Before I do anything else, though, actually, I need to graph one more thing. I need to see where x of t equals 5, not 0. So I actually need to go down here and graph the function y equals 5. Now let me zoom fit this thing and see if I can find those 2 intersection points. So there's our parabola. There's 5. All right, that was pretty easy. Let's go ahead now and find those 2 intersection spots. So second trace, intersect, option 5. Let me arrow over to the left one here. And where's my spider? There it is. Press enter, enter, enter. That's an intersection of 1. Okay, that's nice. Let me do another one here. So alpha trace, intersect. Let's see if we get another nice whole number on the other side for this intersection. So enter, enter, enter. Ooh, 3. Okay, I guess I probably could have factored this thing and moved the 5 over, but whatever, it's a calculator problem. So this happens then at 1 and 3. Awesome. Those are our 2 times now, and those are both measured in seconds, so we better put that in there for units. Now for the second part of the problem, they want the slopes of the lines tangent to the particle's path at that point. So in general, if you want the slope in parametric world here, you've got to do y prime of the number over x prime of the number. So in this case, we're going to do y prime of 1 over x prime of 1 and plug that in the calculator. So here's what that looks like on my calculator. I did alpha y equals to get my fancy fraction here. And y prime, I stored that as y2, so y2 of 1. X prime, I stored that as y3, so there's y3 of 1. Enter. It's about 0.432. So that's the slope at time 1. And notice that I specified here that I'm evaluating my derivative at t equals 1. So that really spells it out what's what. All right, now I need to evaluate my derivative at time 3. So that's going to be y prime of 3 over x prime of 3. Back to the calculator. Now the good news is I can steal my input from before, and all I have to do is just change these 1s to 3s. So that's going to make my life a little bit easier. And then press enter. Comes out to exactly 1. Nice. Okay, so the last part here is the y-coordinate of that point, given that y of 2 equals 3 plus 1 over e. So there's some good news on this part of the problem, because you could potentially be having to find y values at 2 different places. The good news is that they said there's a point where the particle passes twice. So the y value that we get through at time 1 should be the same as the y value at time 3 if we've done all of this correctly. So I'm going to start by saying y of 1 equals y of 3. And now I can just have one expression that gives me both at the same time. So for this, I don't actually know the y function, so I'm going to have to use fundamental theorem with my starting y value and the y prime that they gave me right here. Okay, so what was our starting y value? Well, if you're looking in the original stem of the problem for this, you're not going to find anything. You actually have to go to the problem that we're on right now, subsection 3, and they tell us that y of 2 is 3 plus 1 over e. So then if I want to find y of 1, for example, I need to do this value here, 3 plus 1 over e, plus the integral from 2 to 1, or you could do 2 to 3. It should give you the same number, of, now I need y prime of t dt in there. And this is a calculator question. So let's see what this looks like on the calculator. I've got 3 plus 1 over e, and if you're wondering where you can get e without an exponent, if you do second division, you'll get just an e. Rarely have to use that, but here is a situation where maybe saved a little time. And then we have our integral from 2 to 1. This is y prime, where y2 got entered, dx. All of that comes out to 4, apparently. All right, in calculator we trust.